So let's look at the ideal gas laws kind of from a common sense approach. I drew a turbine. All a turbine is something that we put a fluid into it, and we pay for this fluid to be put into it, and then the fluid is going to hit some blades that are sitting in there. So there's blades inside turbines, and those blades are physically attached to a shaft, and that shaft ends up rotating because the blades hit it and made it rotate. And then as they were hitting it, they end up coming out of the outlet. So this is just a fluid. So all we've paid for is a fluid, like a gas or a liquid. So a fluid in, and then the same fluid comes out. Now, this fluid had an energy in it. It had some inherent energy. Some of that energy was lost pushing onto this turbine blade. Some of it went into rotational motion, and then it has an energy out as well. Has an energy in, has an energy out. But let's think about what changes in as it goes through here. Well, this fluid must have had a pressure here, P1, and it must have a pressure here, P2. Well, but the volume has changed. So it had an original volume, V1. If I look at the original volume here, it's kind of a small volume. And now I look at the volume that it took up here is kind of a larger volume, V2. And if I am messing with the pressure and the volume of fluids, we also know from our mechanical engineering, or at least, or even our common sense, that when we mess with the volume of a fluid, then we often have a temperature change. So there could be a temperature at 1 and a temperature at 2. And what the ideal gas laws, and I'm going to say S in brackets, there's really only one ideal gas law. And what we know is that the relationship between pressure, volume, and temperature holds this true. P V equals N R T, where P is pressure, V is volume, N is the amount of the substance in moles, R is a constant that is describing the substance, the fluid, and T is temperature, pressure, volume, amount, fluid properties, and temperature. And then over here then, and that would be the first pressure, the first volume, the amount of fluid, the type of fluid, and the temperature it started with. And over here, same holds true. PV equals nRT. And we can go elsewhere to find the derivation of PV equals nRT, but we know that that's the relationship in, and that's the relationship out. But what is the same? Is pressure the same? Pressure at 1 is not the same as pressure at 2. We see a different geometry. We see that there's more volume. The volume at 1 is not the same as volume at 2. We can see that from our geometry. And we know likely that the temperature at 1 is not going to necessarily be the same as the temperature at 2, unless some external factors are also added. T1 is not equal to T2. But the amount of fluid that came in must be equal to the amount of fluid that came out, because there's only an inlet here. There's an outlet here. There's no other outlet over here, because then it would be in equals out 1 plus out 2. But it's not like that. There's only one outlet. So whatever came in must be coming out, because there's no other place for it to go. So the amount of moles in must equal to the amount of moles out. And the material properties in must equal the material properties out, because it's the same fluid. So R in is going to equal R out. This is because it's the same fluid. And this is because nothing is lost. All right. So now what I can say is I'm going to rearrange my equations. I'm going to solve for N1R1. N1R1 equals V1 over T1. Okay. And N2R2 equals P2V2 over T2. I just did an elementary rearranging of equations to solve for N1R1, right? And N1R2. But N1R1 equals N2R2, we said, because N1 equals N2 and R1 equals R2. Therefore, P1V1 over T1 must equal P2V2 over T2. So in a way, I'm sort of deriving or at least illustrating the ideal gas law and illustrating that the relationship between the pressure, volume, and temperature relates in this manner here. Pressure times volume times the reciprocal of temperature relates in this manner here. And the scale at which they relate, the ratio at which they relate are equal to one another. So this is actually the ideal gas law. And I'm confident enough to say this is the ideal gas law. Now, most people say the ideal gas law is the with a plural, but that's because people like to break these up and say, if you hold pressure constant, then you know, one of the ideal gas laws is V1 over T1 times V2 over T2. If you hold temperature constant, then P1 times V1 equals P2 times V2. If you hold volume constant, then P1 over T1 equals P2 over T2. Yes, that is true. But that breaks it into three laws, and those are called Boyle's law, Gay-Lussac's law, and Charles' law. So that's why the people say ideal gas laws, but this is the ideal gas law. And clearly, I mean, we can look at those cases, but I don't want you to get muddled up in those cases. But if this is the ideal gas law, then if we do this again, we go P1V1 over T1 equals P2V2 over T2. If I let P1 equals P2, which is constant pressure, then P1V1 over T1 would equal to P2V2 over T2, but P1 and P2 would be the same thing, right? So it would be like P1 on both sides of your equation. If there's P1 on both sides of your equation, then you can cancel out that P1. So then all we're left with then is the relationship V1 over T1 equals V2 over T2. Where you're left with this relationship if you have constant pressure. And you can do the same thing for constant temperature, and it'll just cross out the temperatures, right? And you get this equation. But I don't want to right now. I want to do that, like if I need to do that, then that's what I'll do in my question, right? But that's how you would get three equations from just one law. I did it for pressure. You can do it for temperature. You can do it for volume. If you do it for volume, then the volumes cross out. If you say V1 equals V2, then constant volume process, the volumes cross out. And then the relationship is P1 over T1 equals P2 over T2. You can call that a new ideal gas law if you want to, but it all just comes from the same ideal gas law. So what I do is I go in a test just remembering, I don't even remember this relationship. I remember that PV equals nRT, PV equals nRT, set it equal to one another. Therefore, PV over T equals PV over T, 1, 1, 1 over 2, 2, 2. These are all the ideal gas laws in one. So that's how I approach ideal gas laws.